Hello everyone, my name is Raymundo Cassani. On behalf of my colleagues, I'm going to present our work on finding the optimal filter for PPG-based pulse rate detection. Photoplethysmography, known as PPG, is a non-invasive optical technique that detects the changes in the blood volume that occur at each cardiac pulse. Typically, heart rate is derived from the ECG signal. However, from PPG it's possible to have a good estimation of the heart rate, given the fact that PPG can be measured from a single point, as it could be the ear, the fingertip, or the wrist, and that it's present in many wearable devices. It has gained a lot of attention in the last year. Several studies have compared the pulse rate and heart rate variability, and the general conclusion is that the pulse rate variability is not exactly a surrogate of heart rate variability. However, similar to the heart rate variability, it provides important information about the cardiac status of the person. Like many other physiological signals, PPG signal is affected by artifacts, mainly by movement. These artifacts difficult the localization of the PPG pulse, and with this, the accurate estimation of pulse rate. These are two examples of how artifacts affect the PPG signal. With that said, the main goal of this work is to estimate a filter, the optimal filter to process raw PPG signals to preserve the spectral content that is required for an accurate detection of the PPG pulse. Moreover, we report the spectral characterization of the isolated PPG pulse that, as far as we know, it has not been reported in the literature. The analysis presented in this work was performed with the CAPNO-based dataset. This dataset is comprised of 42 PPG recordings with a duration of 8 minutes from adults and children. We made use of this database as it reports the pulse peak locations that were obtained by an expert rater. First, the raw PPG signal y of t is modeled as a convolution of the pulse signal x of t and the impulse response h of t of a system, plus additive noise. And it has this formulation in the frequency domain. The magnitude square coherence, MSC, is used to explore the power relationship between the input and the output of a system, and it is defined in the frequency domain as this, with SXX and SYY being the power spectral densities of the pulse and the raw PPG signals, and SXY being the cross spectrum between these signals. These spectral characteristics are computed as follows. Under the assumption that the pulse signal and the noise are uncorrelated, the cross spectrum between them is equal to 0. As such, the formula to compute the MSC is rewritten as, and it's further reduced to. Here we can see that the MSC represents the coherent power, this is to say, the fraction of the total power that is related to the input. As such, the incoherent power is computed as 1 minus MSC. The ratio between the coherent and incoherent powers can be seen as the signal-to-noise ratio. Then, the optimal filter to enhance the PPG signal for the pulse detection is the one that enhances this SNR. In this slide, the signal processing steps to find this optimal filter are described. First, for each labeled pulse localization, 2 segments centered at the pulse peak were extracted. One consists in 1.7 seconds and one in 1 second. The first segment constitutes the raw PPG and the second segment is the PPG pulse. Both signals were windowed by a 2-key window, and the pulse signal was 0 padded to have the same duration as the raw PPG segment. As next step, in order to compute the MSC, it's necessary to have estimations for SXX, SYY, and SXY. and these are obtained as follows. Then the MSC and the SNR curves are computed as. Finally, from the SNR curve, we identify the bandwidth of the optimal filter as the bandwidth in the SNR curve at 6 dB below its maximum point. All the codes to perform this analysis are available in this link. Results and discussion. As first result, we computed the mean PPG pulse for children and adults. This graph presents the mean PPG pulse with one standard deviation. It is possible to see that there were some differences between groups. Mainly, the average PPG for the children cohort presents a deeper pulse foot and a steeper slope in the rising edge. Also, the average PPG pulse from the adult cohort was slightly longer. These findings are in line with the age effects on the PPG signal reported in the literature. These figures show the power spectra for the raw PPG and pulse PPG, and the MSC and SNR curves for the adult and children cohorts. From the plots, we identify the bandwidth for the optimal filter and the bandwidth for the PPG pulse. The results show a wider optimal filter for adults and a wider PPG bandwidth in the children group. To obtain a more general optimal filter, we analyze all the data from subjects in the database who are 16 years old or older, and we found the optimal filter to be from 0.6 to 3.3 Hz. In this figure, we have a segment of raw PPG in black and the filter PPG with the optimal filter in green. Filtering is the first step in processing PPG signal to reduce artifacts. We analyzed over 27,000 PPG pulses and found that the optimal filter to enhance the peak detection has a bandwidth from 0.6 to 3.3 Hz. The computed optimal filter can be used in future works as a baseline reference for the removal of artifacts. To the best of our knowledge, this is the first time that the PPG pulse spectrum has been reported. Here are the references used in this presentation. If you have any question or comment, do not hesitate in contacting me. All the codes for this work are available in this link. Thank you for watching and have a nice day.